We would like to welcome you to this tutorial video. We also hope that this video provides comprehensive yet sufficient overview about the installation and use of SAFE tool. This tool is developed as a result of collaborative project between Khalifa University, Abu Dhabi Transmission and Dispatch Company Transco, and Manitoba Hydro International. SAFE refers to stability assessment, visualization and enhancement of power grids. In the literature, power system stability is defined as the ability of an electric power system for a given initial operating condition to regain a state of equilibrium after being subjected to a physical disturbance, with most system variables bounded so that practically the entire system remains intact. Power systems is an important aspect of secure and reliable operation. In addition, instability can cause major blackouts, possibly damage of various system equipments and significant financial losses. In this context, fast and accurate stability assessment is of critical importance to power system operations. Consequently, the designed SAFE tool is intended to serve this objective using the recent developments of machine learning and deep learning techniques. As we can see, the SAFE tool has two main components, the sector analysis and the visualization dashboard. Sector refers to the simulation, extracting, training, optimizing, and response for Abu Dhabi Transmission and Dispatch Company, Transco. In addition, there is the visualization part of the tool, which assists in visualizing the main results through a friendly and interactive user interface. Moreover, SAFE tool utilizes an efficient transfer of data, storing and extracting of results using MySQL database. The sector analysis contains all the written codes in Python that facilitates the simulation of several contingencies in PSSE, extracting .out files into usable data formats among different platforms, in addition to training and testing the transient stability prediction model. Furthermore, the visualization dashboard contains all the files to visualize the results. Once the tool files are copied to your own machine, the codes included in the file contains all the information required to start running the visualization dashboard, and this information is included in the read.md file. We can see that it contains the required information about the tool and how to start the tool. In addition, it contains an overall description about the architecture of the dashboard. The run.py file is another important one, which comprises of all the directories required to run the tool. For example, this code includes the directory which point to the data folder in the visualization dashboard. Also, this directory points to the files copied in under sector. This example shows the directory which points to the simulation folder. The out underscore files and npz underscore files point to the places where the simulation outputs are and the extracted outputs are stored. The user should modify all these directories in order to properly run the tool. Furthermore, the user should provide the MySQL credentials, the username and password, in order to properly communicate with the MySQL database and extract data using the columns in the database. On the other hand, the config file under sector contains also important information about the configuration of MySQL. The user should provide his credentials like the username, password, host, database in order to properly communicate with the database. In addition, the user should modify certain directories in order to store the data once the analysis is completed. For example, the user should provide the directory of the data, which can be copied from the sector files under Save tool and navigate to data, copy the path and paste it in the proper data directory in the config file. The same should be done for models, norms, shared files, libraries, training, and validation logs. Also, the user should provide the proper location for the PSSE. The next step is to configure the MySQL workbench such that the Save tool is able to read and store data from and into the database. To achieve this objective, please choose the right connection in your MySQL connections. And after that, after you log in into your own MySQL connection, we should create a new schema in order to upload the required columns for the tool. This can be done as follows. We should select Create a new schema in the connected server. In this window, the user should provide the name for the new schema. In this case, we will provide the name Transco. In addition, the user should provide the chart set. And in this case, we are using the last one. Also, we should provide the correlation. And in this case, it's the first one. After providing these inputs, the user should apply in order to start creating the new schema. In this code, the MySQL will create a new schema with the provided name. We can see on this terminal that a new schema is added and it's called Transco. However, this schema is empty, as we can see from the tables. To upload the required tables, one should navigate to Server and import data. The user should choose Import from self-contained file in order to upload the required SQL file into the created schema. Once this SQL text is uploaded, one should also specify the default target schema. And in this case, it's Transco. One should click on Start Import, and as we can see, this process finished. Once this process is finished, the user can click on Refresh All, and we can see that the tables are updated, and those tables are required to communicate with the Save tool. They will store the data as an output of the analysis, and they are also used to exchange data, read some information with the tool when conducting the training and testing of the transient stability prediction model. For example, this contingency table, we can see that it contains information about the contingencies. We can see here that it's empty. This table contains information about the contingency, like the ID, the season name, the clean time, branch from, branch to, which are information about the fault, the status to indicate the simulation, the system, and final labels. To start running the tool, we should navigate to the place where you copied the visualization dashboard. In the terminal, we can click on CMD. A new terminal appears. And in this terminal, we should provide two main codes. These codes can be found in the read.md file. The first code is set flask run.py. We copy it and paste it in the terminal. The second command is flask run. It should be also copied and pasted here. But we need to make sure that the flask that is running here is the same that installed under Python 3.8. Therefore, once we copy this code and execute it, a new IP address is created and it's given to the user in order to copy it and paste it in his web browser to start running the tool. We can open the web browser to start running the tool. As we can see, the main login page appears. After logging into the main page using your own credentials, we can see the main page of the Safe tool. As we can see, we have three main parts: sector analysis, fast screening, and DMD analysis. The sector analysis contains mainly of 7 steps. They are enumerate contingencies, simulation, data extraction, data cleaning, training, optimizing parameters, evaluation and response. The fast screening contains also of generate selected contingencies, simulation, data extraction, data cleaning, and testing. The DMD analysis contains of the components which are used to compute the oscillatory modes of the system. Sector refers to the process of simulation, extraction, data cleaning, training, optimizing, and evaluating the response of a transient stability prediction model. The first step in conducting the sector analysis is to generate the set of contingencies which will be used to train the transient stability prediction models. These contingencies contain information about the type of faults that will be used to generate the dynamic response of the system. To achieve this step, one should click on the Enumerate Contingencies tab. The user will be asked to upload the save file of the case, the season name, which will be 2020 max, and the number of contingencies. If the user selects 0, this means that he that all cases, all contingencies in the case will be generated. But if he decides to generate a specific number of contingencies, he can specify it in the main cell. Once these information are inserted, the user can click on Run to start the process of generating the set of contingencies. And we can see here in the terminal that a new window appears. This window shows that the command is fired in the terminal and the execution is done. A pop-up message indicates that the enumerate contingency is completed. To visualize the generated set of contingencies, the user should click on Visualize. As it can be seen from this table, 10 contingencies are generated with the specified season by the user. Also, each contingency contains some information like the cleaning time, the fault location, the circuit ID, and the status. The status for all contingencies are initiated with 0 to indicate that the simulation has not yet started. The set type indicates that the contingencies can be either training or testing. This means that some of the contingencies will be splitted and be designated with the name training to indicate that these contingencies will be used during the training, and the rest of the contingencies will be designated as testing to indicate that they will be used to evaluate the response of the model. The system label indicates the initial transient stability assessment labels which will be used during the training of the transient stability prediction model. This table is connected with the MySQL database. As we can see, we can click on execute the selected portion in order to see the content of the contingency table, and we can see this table is updated using the provided input from the user and with the specified number of contingencies. Once this step is completed, the simulation process should be executed in order to start the simulation of these contingencies, and this step is accomplished using the simulation tab. In the simulation tab, there are also two sub-tabs, simulation and visualization. Under simulation, the user can conduct the time domain simulation using PSSE with the specified input parameters for the simulation. In the visualization, the user can visualize the dynamic response of the simulated cases. To start simulation, one should choose the save file of the case, the dir file, and a set of parameters like the season name, which will be in this case 2021 max, the number of processes, which is selected 1, but the user is given the option to conduct parallel simulation if he has multiple cores. So he can specify the number of cores in this cell to expedite the process of generating completing the simulation. Also, the fault inception time, which is specified as to be at 0.1, and the simulation time will be 0.2. The maximum number of networks iterations, the accelerating factor, and the simulation time step, and the rotor angle reference. Once these inputs are inserted, the user can click on run, and as we can see that the command is fired in the main window. This command calls the Python code which starts the simulation process. To see the execution of the simulation, we should navigate to sector tool under which the simulations, and we can see here that the simulation has started. The first contingency has been created with the out file called contingency 1. The contingency name is given after the contingency ID in the contingency table. We can see the progress of each contingencies. Usually for such cases, the user might be interested to increase the simulation time to allow for capturing the dynamics of the system, and the fault inception time can be chosen to be at 5 seconds. To visualize the dynamic response of a contingency, we can do that from the visualization tab. In addition, the user is given the option to either upload a .out file or to choose from a directory. In this case, we will upload an out file which contains the dynamic response of a contingency. we need to choose the case name, the contingency ID, the feature number, and the season name. The user is also given the option to select one of the features to be plotted. The user can plot the rotor angles of synchronous generators, the rotor speeds, the voltage angle and voltage magnitudes of all buses. We will choose to plot the rotor angles. We can see here a command is fired in the terminal to call the responsible Python code for plotting the dynamic response of the selected contingency. Once the computation is completed, a pop-up message will appear, and the dynamic response will appear in the main page with the specified contingency and its information. In the y-axis, we will see an indication or a label for the relative rotor angles of synchronous generators, and here we can see the number of generators selected, which are 50. In this plot, we can interactively change the intended plot. As we can see, the tool provides a very clear visualization of the dynamic response of the system. The next step in the sector process is to convert the .out files generated in PSSE into a readable format across the different platforms. In this case, the .out files are converted to NPZ Python files. To do that, the user should click on Data Extraction and select the directory which contains So the user should select a directory which contains the simulated cases. In this one, the simulated cases are stored in 2021 Max. The user should define the original sampling rate and the target sampling rate to reduce the amount of storage in the system. Also, the user should select the season name. Once these inputs are defined, the user can click on Run, and as we can see, once the user defines these inputs, he can click on Run, and a command is fired in the terminal which indicates the starting of the conversion process. To access the converted files, we can see that under NBZ, a new file name with a specified case or season name is created. It's 2021 Max, and we can see that all the cases are converted to NPZ files. Once the data extraction is completed, a pop-up message appears to the user to show him that this step is completed. The second step in the sector process is to provide initial labels for the generated simulated contingencies, which will be used during the training of the model. To do that, we should select the data cleaning tab in the data cleaning, and the first step is to finish the process of splitting and labeling the data. This means that all generated contingencies will be splitted into training and testing datasets respectively. In addition, all the cases will be assessed against a defined criteria for providing the initial transient stability labels. So the user should provide the name of the case, which contains all the contingencies that has been simulated. Once click on Run, the process of splitting and labeling the data will start, as we can see from this command. A pop-up message will appear to indicate that split and labeling completed. It can be seen from the contingency table that the new sets have been established, the training and testing dataset, and also the system label is provided to indicate the initial stability status of the system. The next step is to prepare the data for training and testing. This step is required in order to provide the proper pipelines for training the model. In addition, in this step, the data will be arranged into slices in order to be fed to the training of the neural network model. This process should be carried out twice, one for the training dataset and the other one for testing dataset. So for training, we choose the Windows type, and we should provide the season name, the features. V refers to voltage magnitudes, and VA refers to voltage angles. This means that we are extracting the voltage and voltage magnitudes and angles of the buses to train the neural network. We should choose the size, and we should also choose Tmax and the fault time, which is in this case 100. We apply the fault at 0.1 second, and we are simulating at 0.01, which have been defined by the user as the target rate. The set type will be training. We will click on Run. Once the inputs for the data extraction, for the data preparation are completed by the user can click on Run to start the conversion process. And once it's completed, we can see a pop-up message to indicate that prepare data is completed. One can visualize the data in this table, which indicates that a data ID of 1 is designated for the training dataset with the specified inputs from the user. The same step should be done for the testing dataset, and for testing we choose the continuous type, and also we should set the data type, the set type to testing. We can again click on Run, and once completed we can also visualize the testing dataset with the specified inputs from the user. By this we can see that 2 data IDs are created, one is for training and one is for testing. In addition, we can see that a separate data matrix is created in the sector under data. We can see that the training and testing datasets are stored here. They will be called during the training and testing process in the sector analysis. To enhance the performance of the trained model, the data should be normalized. And in order to do that, the user should click on Data Normalization, provide the season name and the set of features, which, as mentioned previously, are taken to be the bus voltage magnitudes and voltage angles. The user can click on Run, and once the computation is done, a message will appear to indicate that prepare normalization is completed. And we can visualize the normalized data using this table, which indicates the ID of the normalized data, the season name, the features taken, which are the voltage magnitudes and angles. Similarly, we can see under sector that these norms are stored here, which indicate the means of the data vector and the standard deviation for the selected data. Once this process is completed, we are ready now to train the transient stability prediction model, and this can be done from the Training tab. The user is given the option to choose different model names. To access these names, we can refer to the models under sector, and we can see that different models can be trained, like the SqueezeNet and Inception network, and these models can be selected from here. So the user can either train a generator inception network, a generator inception network with logistics, a generator squeeze network, a generator squeeze network with log output. In this case, we will choose the generator inception network, GIN. And also we should provide the data ID. This data ID can be obtained from the data table under the schema transco. In this case, the training is designated the data ID 1, so we should use this data ID. We should also specify the number of filters for the neural network. In this case, we will choose 64 and 128. The number of hidden layers, we will choose 128. The number of epochs, which represent the number of iterations over which the training of the model will be carried out. And in this case, we will use 1. The batch size, we will choose it as 128. And the initial learning rate, we will specify it as 0.01. If the user decides not to insert the rest of the values, this means that the default values will be used. However, the normalize should be chosen, and it can be either true to use the normalized vectors or false to ignore the normalized vectors. Once these inputs are inserted by the user, he can click on Run, and the command is fired in the terminal to call the function trainer, the Python code trainer, which is responsible for training the neural net prediction model. A bar will be shown to indicate the completion of the training, and once the training is completed, the pop-up message will appear, and we can visualize the training results from this table. We can see that the chosen data ID is provided here with the provided training model. It has the ID 2 and also the specified parameters by the user. And we can see here the accuracy and loss of the trained model. As we use few number of cases and small number of iterations, the accuracy of the model will be defined accordingly. So in order to improve the accuracy of the model, higher number of epochs and larger data set should be provided. This accuracy is based on only 10 cases, which are generated earlier. Another step after training the model is to see the sensitivity of the model to changes in parameters. And this can be done in the optimizing parameters step. The user should provide the model name, which will be chosen as the previous step, the data ID, which also be chosen as the same used in the training, the number of filters, the number of hidden layers, number of epochs, the initial learning rate, and the normalize will be set to true. Once these inputs are ready, the user can click on Run, and the command is fired in the terminal to call the Python code which is responsible for validating the results. Once the process is completed, the user can click on OK, and the table can be visualized using the Visualize button. Once this step is completed, the model can be tested on unseen data using the evaluation and response step in sector analysis, where the user can test the trained model on unseen data by inputting the training ID, which can be obtained from the training table. In this case, we will use the training ID too. In addition, the data ID will be obtained from the data table in the MySQL database, and we will choose the second one, which is associated with the testing dataset, and we can click on Run to start the evaluation process. A specific bar will appear to indicate the completion of the testing dataset. Once the evaluation for the transient stability of these cases is completed, a pop-up message will appear, and the user can visualize the data from this table, which shows the threshold from 0.05 up to 0.045 and the accuracy and the other important parameters which are related with the testing. As I mentioned earlier, we should use larger data sets to contain larger data in order to improve the accuracy of the transient stability prediction model. For instance, we have used only 10 cases, and only the training is done using one epoch. With higher number of epochs also, the accuracy of the model can be significantly improved. And by this, we finish all the steps required in the sector analysis. The next part of the SAFE tool is the fast screening. The fast screening gives the user an option to test some selected contingencies using already trained models. And in order to accomplish this, the user should first start by generating some selected contingencies. In this case, we will choose the SAFE file, the season name, and we will call it 2021 max testing, and we will specify the number of contingencies, and in this case we will generate also 10 contingencies. We'll click on Run, and once the computation is done, the user can visualize the table using the Visualize button, and we can see additional 10 contingencies are added, which will be used for testing. The simulation of these cases are needed in order to start the testing process using an already trained model. The simulation of the selected contingencies are carried out similarly to the sector process. And we can see here the selected the outputs of the simulated cases. To visualize some of the cases, we this time choose a season name and choose a file name. We should provide a contingency ID, selected number of features, and in this case we will provide the rotor speed as the selected feature. We can click on visualize the case, and the process of extracting the data from the provided .out file starts, as we can see from this command. Once the visualization is completed, we can see the dynamic response displayed in the main page. We can see in this plot that the dynamic response for the first 50 generators are plotted, and on the Y label shows the relative rotor speed of all selected synchronous generator, the case name, and the associated information. As mentioned earlier, the plot provides interactive environment, so you can remove some plots and add them back. The next step in the fast screening is to convert the .out files into readable format across the Python platform, and this is done similar way to the sector process. The user should provide the data directory, the original sampling rate, the target sampling rate, and the season name. Once click on run, the process of converting the data will started, and as we can see here, the converted files are stored under the same case name, which is 2021 max testing. Once the data is extracted, the user can go to the next step, which is data cleaning, to provide the name, the data type, and the test size of the testing dataset. In this case, the season name will be 2021 max testing, and the test size in this case it will be 1, to indicate that all the dataset in the testing will be used for testing. We can see the fired command, and once completed, we can visualize the selected set of contingencies for testing, and they provided the set type, which is also testing, and they provide like the initial system label for comparative analysis. The final step in fast screening is to test this set of contingencies against the already trained model. And as I mentioned previously, we need to provide the training ID, which can be obtained from the training column in the MySQL database. In this case, we will use the previously trained model, which has the ID 2. We will provide the season name, which is in this case 2021 max testing. We will provide the Tmax, which is 20, and the threshold, which is 0.01. The user can click on run. We can see the associated command is fired in the terminal to call the Python code which is responsible for testing. Once the process is completed, the message will appear and the user can visualize the testing results using this table. We can see that the ID indicates the contingency number and the used model name in the training, and the used data ID which corresponds to these contingencies. And we can see the prediction as a result of testing the trained model on the unseen
data. In order to enhance the accuracy of the prediction, we should train the model for larger data set and higher number of epochs, and do different trials to approach to a very good accuracy for the trained models. And by this we finish the fast screening part of the SAFE tool. The final part is conducting DMD analysis. DMD refers to dynamic mode decomposition. It's a model identification based technique which uses a set of measurements contained in the .out file to estimate the oscillatory parameters of inter-area modes of oscillations. This analysis provides the user with the option to access the estimated oscillatory parameters like the frequency and damping ratio of inter-area modes using a selected data feature like the rotor angle, rotor speed, active power. The user can choose the file from a directory using season name. In this case, we will choose the 2021 max, and we will choose the file name or the contingency name, which is 1. We will choose also the initial time for conducting the simulation, for conducting the analysis, and the end time, which represents the time window over which DMD analysis will be executed. Once these inputs are ready, the user can click on run, and as we can see in the terminal, a specific command was created to call the responsible code for conducting DMD analysis. Once the computation is completed, a specific message will appear to the user on the main page to indicate that the analysis has completed. The user can access the results from the visualized table, and here we can see the oscillatory parameters estimated by the DMD. Those parameters are the mode frequency and mode's damping ratio. We can see that the frequency of these oscillations are less than 1 to indicate that we are interested in the inter-area modes of oscillation. In addition, it gives us the mode's damping ratio for each frequency. We can visualize also the dynamic response of the selected features over the specified time window. Here we took only the time window from 5 seconds to 25 seconds. And here we can see in the interactive tool that the dynamic response of the case was plotted, where we can see some oscillations that corresponds to the estimation of the DMD analysis. So the user can compare the DMD results with the plotted dynamic response to investigate the results of this analysis. As we can see earlier, we have tested the SAFE tool, and we have shown its use through live demo. We have shown the use of sector analysis, we have shown the fast screening, and finally the use of DMD analysis for estimating the oscillatory parameters of inter-area modes of oscillations. I hope that you find this tutorial useful in the use of SAFE tool and in conducting the provided analysis, whether it's transient stability prediction model, fast screening, or estimating the presence of poorly damped oscillations.